Right, so this is Math466, Advanced Applied Analysis. This is Lecture 4. So we're going to start today by discussing the homework problems. What I want to do is I want to discuss the theory behind the linear regression approach. So amazingly, I'm not sure if this is good or bad, but my most influential posting in my entire academic career is a set of notes I wrote on the method of least squares when I was a postdoc at Brown. That's been downloaded more than anything else according to various metrics. And I frequently get emails about this. It's basically a proof of the linear regression formula as to how do you find the best fit coefficients. So we're trying to solve for y as a linear combination of some x. So the general framework is we have, y is, some matrix of data x times some unknown coefficients beta. And what we're going to do here is the y's will be slices of time. So you'll have the first entry will be time 1, time 2, time 3, time 4, time 5, etc. And so x will have a different row for each time, and the rows will have the values of the different things. So if we're doing schools, it could be the populations of the 3 schools followed by the net worth of the towns. We will also have the first column of x be all 1s. So the formula we're going to be looking for is we want, y at time n is going to be beta 1 times 1 plus beta 2 times the Lanesboro Elementary School population plus beta 3 times the Williamstown Elementary School population plus, at time n, times beta 4, the Mount Greylock population at time n, plus beta 5, basically the net worth or property value of Lanesboro. I guess it should be Lanesboro equivalent value at time n, plus beta 6, Williamstown's net worth at time n. So this is a very natural, simple formula to look at. I'm looking at a linear combination of these quantities. I'm trying to find what values of the betas give me the best fit with the observed data. So I have a bunch of years of data where I have the values of all these numbers, and then I have how much money went to Williamstown Elementary from the state, Lanesboro Elementary from the state, Mount Greylock from the state. Well, I can add up that and see how much total money went to all 3 schools and see what percentage went to Williamstown, what percentage went to Lanesboro, what percentage went to Mount Greylock. So I will have my outputs here will be percentages. So this will be percent in year n. And I really should do this 3 times. I should do it for Williamstown, I should do it for Lanesboro, I should do it for Mount Greylock. And so here, I should put a subscript I, which will be 1, 2, or 3. I equals 1 will be Lanesboro, I equals 2 will be Williamstown, I equals 3 will be Mount Greylock. So there's 3 regression problems to solve. What's nice is they all have the same data matrix. It's the same x for all of them. What changes is the amount of each. So we do not know the formula the state uses. We're trying to estimate the formula. Now the nice thing is the theory of regression. So I'll call this I now, and I'll put it beta I. We'll do I is in 1, 2, 3. The best fit values is going to be beta I is x transpose x inverse x transpose. I'm pretty sure that this is, do I have drop the first x? Okay. Yes, I drop the first x, yes. So this is the solution. And then when I plug in to see the estimate, if I want to estimate what that number should be, that's where the other x comes in, because now I put in the betas, yes.
So setting up the problem this way, it implies the state has 3 separate regressions for each school has a different regression for calculating funding?
Correct. Well, and then it's actually a little bit worse because the state has more variables in play than just these 5. And so we're trying to find a simple formula that's reasonable, that's accurate.
What about doing one regression for all 3 schools and having the school as a variable?
then what's our output going to be?
Just like funding in
Number of dollars.
and then you would scale it either some to get percentages.
So it's going to turn out that this will actually have as a result that the 3 percentages always sum to 1.
Okay.
So there's a couple of different ways you could write them, but because of some of the structure of X, it turns out that I think a lot of these are equivalent. The real question is, do we want as output a number, or do we want as the output as a vector? The vector could be the splits. And in fact, we don't even need 3 numbers for the splits, we only need 2 numbers. If we only had 2 schools, it would be a lot easier, because then you only need to know what % goes to one school, because the other school just eats up everything else. So here, our best estimate is now we plug this in for the betas, and now we get X transpose X inverse X transpose YI. And so we had a couple of questions. So I should never have given away, I should have printed out 6 solution keys and not 5. So let me just quickly punch up my solution key here so I can see what the different questions were. So the first question I asked was, okay. Does the solution exist? So if we actually go through this, will we always have a solution? What do you think? So what could be the danger?
I have a semi-related question.
Sure.
So talking about smooth regression this way, does this allow the state to value growth in different areas?
Differently.
Yeah.
Yes.
That's more like, I guess, the intention of doing it.
That's the intention, because $1 in Williamstown in terms of property value may not be the same as $1 change in Lanesboro.
Right.
And so the idea is to use a small number of variables that capture what's going on.
Right.
And so in the current apportionment for building costs between the 2 towns, we just use population and we just use essentially assessment. It matters in some sense what you mean by population, because some students are transferring into the school district. So I'm being a little bit crude right now. And I'm quite interested to see what you've written. But over here, is this always going to give me an answer? So okay, I see you shaking your head. What could be the trouble?
If X transpose X doesn't invert.
Yeah, so is X transpose X always invertible? So if one of the rows of X is repeated, and we have a different value, then we know we're in trouble. Now, fortunately, in any real-world problem, so long as things are small, the odds that you will have a dependency is quite small. But it is a possibility. Do we actually have to worry about it? Well, we can actually do the calculation. We can see for our numbers it's invertible.
When you're finding beta I for a specific school,
Yes.
is your X matrix of examples from all 3 schools, or just that specific school?
Well, what we're using for our X matrix is just the populations of the 3 schools and the property values of the 2 towns. So the X matrix is the same for all schools, because all we care about is the number of students in each building and the value of the 2 towns. If you were just trying to calculate what's going on at Lanesboro Elementary, you might say it doesn't really matter what's going on at the high school, and it doesn't matter what's going on at Williamstown Elementary. And so you might have some extra variables in play for Lanesboro Elementary that don't really matter.
Aren't each of these regressions trying to determine what's going on only at one school?
Correct, but I can still consider, yes.
So we can end up doing, like, maybe to like make this into like one regression, we can have our Y vector be like an n by 3.
Mm-hmm.
And that gives us like 3 columns of like
right, but if you do a Y vector as 3 columns, it's essentially doing 3 regressions.
I agree.
Yes. It's just a question of how you want to phrase things.
Right.
And I want to keep the phrasing as close to the standard linear regression as possible in terms of communicating. But you're absolutely correct that you could do the problem just looking for Lanesboro Elementary at just its population. And so now when I have something like this, the question is, when is X transpose X going to be invertible? Well, if, let's say X is R by C. So this is going to be a C by C matrix. So I need the columns to be linearly independent. So we're okay if the columns are linearly independent. And in general, you should have more rows than columns. You'll have more years of data than you will have variables. Imagine we only have 2 years of data and 5 variables. Then you're going to have so many possible solutions. It's going to be an underdetermined system. So in applications, you will have more data, and you're trying to find the best thing you can with that. So we will almost surely be okay that this will be invertible. So it will satisfy at least the first requirement. The second requirement was, will the percentages always be between 0 and 1? And unfortunately, if you deviate enormously, it is possible that the percentages might not be between 0 and 1. And then the real question is, do we actually include something like this in the regional agreement to say that if the percentage is negative, you just floor it at 0 so that you don't have one school stuck paying? But the next question related to this is it stable under small changes? Yes, because it's a linear combination. If I have a small change in the values, there will be a small change in the prediction. Yes?
What if your coefficients are really large?
Then that just affects what the definition of small is. So no matter what the coefficients are, they're fixed. And so if the change is sufficiently small, it will not be a huge change in the percentages. But the definition of, or what it means to be a small change, will be a function of the values.
Do you define it as a function of the L1 norm of beta?
Sure. And basically, as long as you're moving less than like the maximum, I don't know if I'd use the L1 norm, I might use the L infinity norm, the largest value of the betas. And if you look at 1 over the largest value, or maybe 1 over 100 times the largest value, then you'll move by at most 1 over 100. So you move by at most 1%. So something like that would tell you how far you can move. The last one is the most important, is will these sum to 1? So did anybody have a way to show that it will always sum to 1? That we're not going to allocate more than 100% of the pie, and we're not going to leave any pie on the table. What you could, of course, always do is you could say, let's figure out what percent goes to each school, and then let's add up those 3 numbers. And then Lanesville gets its percent divided by that sum, Williamstown gets its percent divided by that sum, and Greylock its percent divided by that sum. And if you do that, then you'll be fine. However, if it always adds up to 1, there's no need to spend the time doing that division. You're going to complicate the formula needlessly. It's going to look more involved than it actually is. So can you prove that these 3 regressions will always sum to 1? So this is where it's really nice that we have the same matrix every single time. Nope. All right. Let's try doing it the old-fashioned way. Okay. So we have our formula. So we have yi estimate is the following. So it's going to be x transpose x inverse x transpose yi. And each of these yi's is going to be a percentage between 0 and 1. Let's sum all of them. If you sum all of them, what do you get for the sum of the yi's? Yeah, or just 1 for every year, right? Because the 3 percentages that sum to 1, this is the observed data. We observe 100% being divided. So if we sum, I goes from 1 to 3 of our estimate, it's going to be x transpose x inverse x transpose times the vector of all 1s. Okay, so this is a matrix. Let's call this matrix M. This is a C by C matrix. This is an R by C matrix. This is the transpose. This is a C by R. So this is a R by R matrix. And we're applying this R by R matrix to 1. What do we hope we get back? What do we hope we get back? An R by 1 matrix, which is all ones. Right. So we want 1 to be an eigenvector of this matrix with eigenvalue 1. So it all comes down to what are the eigenvalues and eigenvectors of M. So can anybody look at this matrix and see eigenvalues and eigenvectors? So what are the eigenvalues and vectors of M? And so remember, M is X transpose X inverse X transpose. Okay? If you could multiply this by anything on the right, what would you love to multiply this by on the right? X. So let's just calculate M applied to the matrix X. That will be X transpose X inverse X transpose X. What does the right-hand side simplify to? X. So you've just shown that Mx equals X. Can somebody interpret what Mx equals X means?
One is an eigenvalue.
Okay, and what's the eigenvector? Yeah, each column of X is an eigenvector with eigenvalue 1. So each column of X is an eigenvector with eigenvalue 1. We're almost done. All we have to do now is show that 1 is in the column space of X. It's the first column. I was writing this up at my son's baseball practice last night, and I was having trouble for a while proving that 1 was in the column space until I remembered, oh, the first column is all 1s. So as first column is just the vector that's identically 1, we're done. So this does prove that no matter what, the percentages will at least add up to 1. Okay, so I'm very interested in reading your suggestions and your thoughts as to how you would want to attack this. There are a lot of ways to attack a problem like this. You want something that is fairly accurate, easy to use, easy to explain. And you want it to have a bunch of desirable properties. So the homework problem was, here's a bunch of desirable properties. It does not have every desirable property. It is possible it could give a negative percentage. That's bad. The other thing which you would like is maybe things should go in the right direction. If maybe there are more students in Lanesboro, maybe Lanesboro should be getting more money. So you can look at, do the parameters go in the directions you want them to? Okay. The second problem, I was not expecting to still be of interest right now. So what was the second homework problem? Yeah, the $75,000 insurance policy on the Indians' win streak. So I gave that to you on, was it Friday of last week?
Yeah.
Yes. It's now a week later, and the Indians have still yet to lose. Something like that. It's incredible. So the Indians were trailing 2-1 going into the 9th inning at home last night, scored a run in the 9th, scored another run in the 10th, and won the game 3-2. And so they're now at 22 straight wins. I think that's now the record in the modern era of baseball. The grand record is, I think, 26 games, but that includes a tie. And that's just not right.
It includes a tie?
So, okay, so in the old days, you could have a tie in baseball. A commissioner, Bud Selig, decided that this would be like the sign of the apocalypse if there was a tie in baseball. Baseball just cannot handle ties. And if a game has been going on for 20 innings or something, we'll just pause the game and we'll continue it later if it gets too dark. Baseball will no longer have ties. We do not have enough time in this class to go into why it is such a catastrophe for baseball, unlike other sports, to have a game ending in a tie. We will just have to accept on faith that this is bad, and we will adjust the league accordingly so that this catastrophe never happens again.
So why would they include that in the kind of...
So the question is, what is your streak for most consecutive games with a win? Is not the same question as what is your streak for your most consecutive games without a loss. So if you look at the streak of the most consecutive games without a loss, it's 26. If you look at the most consecutive games with a win, it's now the Indians at 22. So they're slightly different questions. For those of you who like baseball, a really good question is, which is the most impressive streak of a hitter in all time? Anybody know what the two candidates are? Ted Williams, which in my mind is the more impressive one. And the other one?
I would guess Barry Bonds.
No. Joe DiMaggio.
Yeah.
So Joe DiMaggio hit, I think, in 56 straight games.
Oh, and he had like there was like a month where he had like 100 and some odd RBIs.
Right.
Some absurd
Right.
number. That's like the untouchable 1 month RBI record.
Right.
It's like, well, like.
But Ted Williams has over 81, I think, straight games of getting on base. So basically, for more than half the season, he got on base every day, at least once. And so the question is, which is the more impressive achievement? To have a physical hit or to have a walk? I was actually talking with a former commissioner of Major League Baseball. I love being able to say that. He is a Williams alum, loves this place. You can probably figure out who this is. And he told me that he was talking years ago at DiMaggio's funeral to, I think, one of his teammates. And this was when DiMaggio was in the 30s for the number of consecutive games in a row with a hit. And it's like the 8th inning, the Yankees are playing at home, they're up by 1 run, the first guy gets out, next guy gets on first, the batter comes up and he goes, oh crap, if I hit into a double play, the DiMaggio who's batting next after me won't get up. If we hold in the top of the 9th, DiMaggio doesn't get any more at-bats and he doesn't have a hit today. I've got to make sure I don't get into a double play. So he asks the manager for permission to hit a bunt and basically just sacrifice himself to make sure DiMaggio gets to bat and has a chance to continue his streak, and DiMaggio gets a hit in his at-bat, and the streak continues. This guy also deliberately struck out in a World Series game because it was a wild pitch, and if you strike and the catcher does not catch the third strike, if first base is available, you can run to first. And so he noticed that if he chooses to strike out, he can actually get on first. Baseball. Yes.
So if it's like 1 and 2, and you.
And it's a wild pitch.
Swing at a wild pitch, you can take first base.
If the catcher doesn't catch it, yes. If it's a dropped third strike.
Otherwise, it's just ball 2.
Otherwise, it's ball 2. So look up dropped third strike. When I was young, I saw Dwight Evans do that once for the Red Sox. Baseball has some strange rules. Earlier this season, the Red Sox were losing, and it was the bottom of the 9th at Fenway, and the batter struck out. But the catcher dropped the ball, the batter runs to first, and I think the next batter hits a 3-run home run, and the Red Sox win. They should have lost the game, it should have been over. But the dropped third strike. So the question here is, what is the correct value for the insurance of the Indian streak? So it's how much to insure, say, it was like $1,700,000 in sales against 15 or more straight wins. It's not, well, if the Indians win exactly 15 games in a row, then all your purchases are free. But if they win 16 games, you have to pay. Now, as long as there's at least 15 wins in a row, all your purchases in July are free. Now, one of the problems for the insurance company is you don't necessarily know ahead of time how much are you insuring. So if you were the insurance company, what's the first thing you'd want to figure out?
How much did you sell last year in July?
So how much did you sell last year in July? Do you think you will sell the same amount in this July as last? Why not?
We'll sell more because of the promotion.
Right, so the first thing you would have to do as the insurance company is try to estimate what kind of boost in sales do we think we're going to get by this promotion. Do you think it will double sales? Do you think it will triple sales? Do you think sales will increase by a factor of 10? Because you need to figure out how much is the insurance company on the line for if the Indians win 15 straight. So let's say you sold $1 million last July. And let's say the economy is roughly the same now as it was last year. So you might say, well, if all things being equal, we expect to sell $1 million again this July. But now there's this promotion. So now a lot of people say, you know, yeah, if the Indians win 15 in a row, it's free, why not? Let's gamble a little bit. Let's have some fun with our furniture. So do you think that furniture sales would increase by a factor of 10? Do you think that many more people are going to choose to buy expensive couches, love seats, beds, stuff like that? 10 seems excessive. Do you think there'll be at least a 20% increase? I think a 20% increase is quite reasonable. So then, for those of you who are considering consulting and careers like this, one of the questions they will ask you is, how would you estimate how much you might have to insure? And what you could do, of course, is you introduce free parameters. Let's say that it increases by a factor of r, and then we have our answer at the end of the day as a function of r, and then you can just plug in different values and see. So how did people try to attack this problem? How did people try to estimate the probability of 15 straight wins? Yes?
So I looked up, there's a closed form solution for determining like the number of case successes and n Bernoulli trials when you have like a definite independent p probability.
So k successes or k consecutive? Okay.
Consecutive successes, a run of k, yeah.
Okay.
And from there you can, it's a closed form solution, and you can, so I guess the assumption I made was that the $1.7 million was a known quantity.
Right, which is fine.
And therefore I looked at the probability of,
because just as a quick aside, what you can do is you can say the following. We'll structure the contract as follows. You will tell us at the end of July how much you've sold, and then we will multiply that by a fixed percentage for the insurance.
And I looked up a bunch of different preseason predictions for the strength of the Indians.
Okay.
With the 58% win
Okay.
percentage for any game. I assumed independence,
Right.
which isn't a great assumption.
Nope.
Considering there are like 3 or 4 consecutive games against the same team.
Right.
As well as pitching rotations,
Yep.
things like that. But I think for the sake of this problem, it was an okay assumption.
Yep, so this is called the first order solution. Now you've got to be very careful. My brother used to live in an apartment building where to get onto the main street, you had to wait at a traffic light that was red for just an incredibly long period of time. And I believe he was stuck at that light when the Red Sox hit 4 home runs back to back to back to back. He was there for at least 3 of them, just waiting for the light to turn. If you were trying to calculate what's the probability of 4 straight home runs, the simplest thing you could do is say, well, every batter has the same probability of hitting a home run. Well, which is better? To have 2 batters who have 20% chance, let's say everybody has a 20% chance of hitting a home run, or the first 2 have a 30% and the next 2 have 10%, or 40%, 40%, 0%, 0%. On average, they all have the same ability to hit home runs. You're never going to get 4 straight home runs in this situation. I think the all 20% actually does much better than the 30, 30, 10, 10. It's well, it's going to be 2 times 2 times 2 times 2 versus 3 times 3 times 1 times 1.
Yeah.
So this is 16 versus 9. So it's almost twice as likely.
Sure.
And so if you assume that all games are equally likely to be won, it's not a great assumption, but it simplifies the math enormously.
Yeah. So from there, you can get a closed form, right? You can write a function to calculate the odds, and then you can back out what like a fair value would be for the insurance policy, and then
So you would calculate what's the probability that it happens.
Yeah, assuming like 58%.
Sure.
And then you can plug in the $75,000 number as price and back out the premium on this
Right.
win probability that the insurance company is taking to cover this variance.
Okay, so we would do this basically like an expected value calculation.
Right.
We would say, if the probability W sub 15 that we win 15 or more straight, then the expected value
Is like, the number?
well, I mean, then you would just do the calculation. So
Yeah,
how much
it's
would the
around-
insurance company
it's a
pay?
little over $9,000.
For the insurance is,
Assuming fair pricing.
right, is we would have to pay 1.7 million with this probability,
Yeah.
and we would pay nothing
The rest, yeah.
with the rest probability, and we always get the premium. And then you just choose whatever that premium is to make this equal 0. Well, if you're the insurance company, do you choose the premium to make this equal 0? No. The phrase is someone has to pay for Mr. and Mrs. Smith's suits. The insurance company is in business to make money. So you would choose this to be 0, and then any premium above that would be fine for the insurance company. And so you got a value of about 9,000?
That's the priced fair value.
Okay.
To make the EV 0.
Okay.
So what I did was I backed out the win probability. What the probability would be for the expected value would be $75,000.
Right.
And that's like 68%.
Right.
Right, which is approximately 10% premium of like true 10% probability premium, or it's 17% of the true value,
right,
which is a pretty exorbitant
yes
premium.
So from calculations like that, it seems like this was a reasonable amount of money to be charging.
Yeah.
Now, how did they get that formula? How did they get that explicit formula? How clean does it look? So you've got it in here.
When I was looking online, I found that there wasn't a closed form solution.
There is a closed form solution, but it is ghastly.
Yeah, it's ghastly, and then there's ways to do dynamic programming to.
There's this really gross generating function.
Yes.
Where it uses the sum.
Yeah, that.
Like you don't want just the sum, you want the.
Well, so what I want to do is I want to show you two different ways to attack the problem. The first is just computer simulation. Is just take a 162 game season, and then for each game.
It's just 58 games actually we're looking at, right? Because it was after August 1st.
Right. So I'm saying, and so that actually makes it even better for the insurance company.
Yeah.
But let's give the Indians the whole season. Okay? And so let's calculate what would happen. So for a 162 game season, you keep track of what's your consecutive wins by the Indians. And if you win the game, you increment that by 1. As soon as you get to 15, you say it was a successful season, they won 15 straight, and you abort the calculation. And you increase your counter by 1. And if you ever get a loss, then you reset the win streak to 0. And if you make it all the way to the end of the season, well, I guess technically you could stop 14 games before the end of the season, or 13 or whatever, as soon as you get one of those losses. And so you can do this a million times, and you can estimate the probability very well. So if you don't know any math theory, just running some simulations will give you the answer, or a really good approximation. You can do a million simulations of a 162 game season. And for all practical purposes, that's good enough. So that's one way to do the problem. The other way is to do recurrences, and this allows me to share some of the artwork I've made with my kids. So my kids wanted me to save only 2 things from my old office: the basketball net and the little plastic mat for us to do art projects on. So these are the Fibonacci's. They can spiral together, and they form a really nice theorem that the sum of the squares of the Fibonacci numbers up to the nth Fibonacci is the nth times the nth plus first. So in my new office, we actually made the 55 by 55 square. The next Fibonacci number up to 55 is 89. So it would be a massive project to make the 89 by 89 square. But a generalization of the Fibonacci's solves this problem. So what I want to do is, how many of you have seen a lot on recurrence relations? Okay. So how many of you thought to solve this problem with recurrence relations? Okay. So recurrence relations is a terrific go-to topic. So let me just see how things. Okay. So there are 2 things we can calculate: the probability the Indians have a 15 consecutive game win streak, or the probability they don't have a 15 game win streak. Does it matter which one we calculate in some sense? No. If we know one, we know the other. We can subtract from one. It turns out one of them is technically easier to calculate. It's easy to calculate the probability they do not win 15 consecutive. So let's let xn be the probability do not win 15 plus straight. So this means 15 or more straight wins. Yes.
So I was thinking about trying to approach it this way, and I determined, or I felt that order mattered, because at some level, I mean, it's very
What
different.
order?
Order of like games, if you like don't win 15 straight,
Mm-hmm.
matters, because if you like lose the first one and then win 14 and then like find another block of games in which
Right.
you don't win 15 straight and then it opens with a win, then you have a block of 15 that.
Right, so we have to be very careful as how we look at streaks. So xn is the probability we do not win 15 straight. Can anybody tell me the value of for any choice for some n? For some n, it's very easy to calculate the probability we don't win 15 straight. What values of n is it really easy to calculate the probability you don't win 15 straight?
N is the number of games.
N is the number of games you've played.
Yeah, so if N is less than 15.
Yes.
Yeah.
So x0, x1, all the way up to x14 equals 1. If you do not play 15 games, you are not winning 15 straight. The first one that's interesting is, what's the probability you win 15 straight? Well, let's assume you have probability P that you win a game. So the probability that you win 15 straight in your first 15 games is just P to the 15. If you win 15 straight or more in your first 16 games, you could have P to the 16 plus P to the 15 times 1 minus P plus 1 minus P times P to the 15. Now you're starting to have lots of different combinations. We can set this up as a recurrence. Let's consider playing n plus 1 games. What's the probability we win at least 15 if we play n plus 1 games? Well, what's the possibilities? We could lose our last game. So imagine we lose our last game. Now that we've lost the last game, what's the probability we win 15 straight in the remaining n games? X sub n. So we lost our last game, and then we had to have won 15 straight. Well, maybe we won our last game, and we lost 2 games ago. Then it'll be xn minus 1.
Wait, what's the notation for x? What does xn mean?
Xn is the probability we do not win.
I mean, like, so you said in the remaining xn games.
In the remaining n games. So
Those are before it?
yes, look at the very last game. We're looking at
If we lose this game.
Yes.
If we lost.
If we lost the last game, then we had to have won 15 or more in the previous n.
Right.
And the probability of that is xn.
Okay, great.
Or we win the last game, we win game n plus 1, but we lose game n. Then we have to win 15 straight in the first n minus 1 games. I'll do 2 more. Or we win our last 2 games, lose the game before that, and then it's going to be xn minus 2. And we just continue all the way down. And then notice we have a p squared. We have an n minus 2 here. So we could win our last 14 games, lose the 15th game. Do I have to worry about the next term? And that's why we're calculating the probability we do not win 15 straight. Because we've now gone through, we've won our last 14 games. The next branch on the tree is we've won our last 15. What is the probability we do not win 15 games in a row, given that we've just won 15 games in a row? It's a big 0. If we were calculating the probability that we would win 15 games, then this 0 would be a 1, because then it would be a certainty. And it turns out that there are nice ways to solve recurrence relations like this. You basically guess, xn is r to the n, you get a characteristic polynomial, you get linear combinations. Now, unfortunately, this would be a characteristic polynomial of degree 15. We don't want to solve a polynomial of degree 15. How can we solve this? So you could use the characteristic polynomial. You'll get x to the n is r to the n. R to the n is going to satisfy a certain polynomial equation. You will have like 14 or 15 roots to that. You will then have to figure out your linear combination.
Wait, what are you calling a polynomial?
Well, so if you guess x to the n equals r to the n, you'll get r to the n plus 1 equals 1 minus p r to the n plus p 1 minus p r to the n minus 1 plus p to the 14, 1 minus p r to the n minus 14 equals 0. So let me just show how you would do this for the Fibonacci's. So for the Fibonacci's, we would have fn plus 1 is fn plus fn minus 1. We guess fn is r to the n. We then get, if this is true, we get r to the n plus 1 equals r to the n plus r to the n minus 1. Divide both sides by r to the n minus 1. You get r squared equals r plus 1, or r squared minus r minus 1 equals 0, or r equals 1 plus or minus root 5 over 2. And so if you guess r to the n, it's a solution. If I multiply this by 5, it's still a solution. It's a linear relation. If I add two solutions, it's a solution. So the general solution is fn is c1, 1 plus root 5 over 2 to the n, plus c2, 1 minus root 5 over 2 to the n. And then I can figure out what c1 and c2 are because I know what f1 and f2 are, or f0 and f1. And then you use, f0 equals 0, f1 equals 1, and that will tell you c1 is 1 over root 5, and c2 is negative 1 over root 5. And you get an explicit solution. We could, in principle, try to do the same thing over here, except this would be a nightmare. This would be a polynomial. We go down here of n minus 1, and the degree of that was 1 higher. So this would be a polynomial of degree 15. There would be 15 roots. We cannot write down in closed form the solution in 15, which is why I'm very skeptical that there's a...
Yeah, it's not just, it is a recurrence relation.
It's a recurrence relation. So we don't want to solve this in closed form, but we don't need to. The season's only 162 games. This tells us how to just march down the list. So we know the first values all the way up to the first 14 games. So now to calculate x15, we just take a linear combination, then x16, then x17, then x18. The computer can do this, boom, 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 boom. Can just march down without any trouble. And it will tell you what the probability is of a 15-game or more winning streak in 162 games. So we're not going to have a closed form expression, but we're going to have the ability to calculate the exact answer very quickly. And there will be no approximation. There will be no painful numbers to look at. Yes?
What if you do xn plus 1 over xn?
Mm-hmm.
Most of the x's would cancel, right?
No, because this is now xn plus 1 over xn. So you would want to basically say that this looks like 1 over r.
Right.
And then this would be like maybe 1 over r squared.
Right.
But then you still have to figure out what, that's only going to be negligible if r is huge. And so each Fibonacci number is approximately the golden mean times the previous, but when the numbers are small, the approximation is not that great. So it could take a while before things kick in. So there are ways to try to estimate what the largest root is, and frequently the largest root governs the behavior, but not always. So I could choose different values for f0 and f1 to make c1 equals 0, and then it's going to be a very small sequence of numbers. But for this problem, we can actually just march down and calculate the answer exactly. So these are the things I want you to be able to get out of this class, then leaving Williams. If you have some kind of real-world problems, how would you attack it? What are the different kinds of techniques and methods? What are the advantages and disadvantages? You can simulate the answer extremely well. So the first thing I did is I just wrote code to simulate. And then I tried to solve the eigenvalue equation explicitly using Mathematica, and Mathematica basically had some very strong language for me. I think it was red, to really emphasize how Mathematica felt about trying to find. I said, all right, don't try to solve it exactly, just try to approximate the roots of the polynomial. And it was still unhappy. Then I said, well, why don't I just do it like this and march down? So you really want to get a sense of what is required to solve the problem for the application you have in mind. And in many problems, something like this is going to run so fast, it doesn't matter. We're not going to have a billion-game season. Now, what do you think the chances are if we have a billion game season?
Pretty good.
Pretty good. What you can then do is you can then break the billion game season up into blocks of length 15. Each block is independent, and this will give you a lower bound. Because it's possible that your streak starts at the end of the first 15 block and continues into the second. So if you want to get a lower bound for the probability, what you could do is you could divide 162 into blocks of 15. Exactly. And
Do you think that'd be really close?
no, no. If you want to do like lengths of 5, it's not horrible, but it's still bad. Just for having a run of length 5. So I am hoping we will be able to continue talking about the Indians' win streak for maybe another week, and so that they break the 26.
Hopeful not, because it doesn't really help Chris Sale's Cy Young case.
I know, but
No, it's
when you see excellence like this, it's worth appreciating it. But